This is the second part of Model 24, Chemistry of Life, Organic and Biological Chemistry. By the end of this model, you will be able to draw the structures of the functional groups, the alkenes, alkynes, alcohols, haloalkane, carbonyl, ether, aldehyde, ketones, carboxylic acid, esters, amines, and amide. All of these are functional groups. You will be able also to predict the oxidation products of organic compounds. And finally, you will understand what makes a compound a chiral and be able to recognize a chiral substance. So let's talk about the functional groups. The functional groups basically are that part of the molecule that is reactive. Okay, it's basically the functional group. R represent the alkyl portion, CH, of anorganic molecules. And here we have all of the common functional groups. We have seen in the previous model the alkene and alkyne, the double bond and the triple bond. If a molecule has a double bond, it's an alkene. If it has a triple bond, it's an alkyne. We're going to talk about alcohols, that is OH, ethers, haloalkane, amines, aldehyde, ketones, carboxylic acid, esters, and amide during this module. So let's start with the alcohols. The alcohols contains one or more OH group, the alcohol group, or the hydroxyl group. They are named from the parent hydrocarbon. The suffix is changed to OL. You have alcohols, so the end of the name is going to be OL. And a number designates the carbon to which the OH, or the hydroxyl group, is attached. So for example, here we have 2-propanol. We have the largest chain that contains the OH is 1, 2, 3, so it's propane. But because it's an alcohol, because we have OH, the suffix must be OL, so it's propanol. And this is in position 2 because it could be in position 1. If it were in position 1, it will be 1-propanol. Okay, so because of that, we need to number the position of that alcohol. If it could be 1 or 2. Also, we have 2-methyl 2-propanol. We have 1, 2, 3. The largest or the longest chain that contains that OH is a 3-carbon chain. So it's propan and it's OH propanol. And also we have a 2-methyl group, a methyl group in the position 2. So we have a 2-methyl 2-propanol. Here we have a diol. We have 2 OH groups in position 1 of 2 and 2 of an ethane. So it's 1,2-ethane diol because we have 2 OH in position 1 and position 2. Also, we can have an alcohol attached with an aromatic hydrocarbon as this one. This is called phenol. Okay, it's a aromatic ring with an OH. It's called phenol. We also have compounds that could have 3 OH. That's why you use the triol suffix instead of OL. It's triol, and it's 1, 2, 3. The chain is propane. Okay, propane triol, and the position of the alcohols is 1, 2, and 3. So it's 1, 2, 3 propane triol. Also known as glycerol or glycerine, the most common names for this. And the last one, this one is cholesterol. Cholesterol is a really large molecule, and it has an OH. Okay, this is basically the number, the name in UPAC. This is the common name, the cholesterol. So there are some common properties and uses of alcohol. First of all, they are polar molecules. So because of that, they lead to water solubility and also to have higher boiling points. So these will have higher boiling points that, for example, alkanes, alkynes, and alkenes. Also, we're going to mention a few examples and the uses. Methanol is used as a fuel additive. We have also a very common one that you may know, this ethanol, that is used in alcoholic beverages. We have the ethylene glycol. This one is used as an antifreezer in the cars. The glycerol is another one that is used for cosmetic skin softeners and also for food moisturizer. We have the phenol. This one is has been used for making plastics and dyes and topical anesthetic in throat sprays. And also one of the most common also is the cholesterol. This one is an important biomolecule in membranes, but can precipitate and form gallstone or block blood vessels. Another functional group is called the ethers. Sorry, this one is ROR. Basically, this is the basic structure: an alkyl group, oxygen, and alkyl group. This could be any alkyl group of any long chain of carbon, as well as this one. They could be the same, but they could be, for example, methyl and methyl, or they could be methyl and ethyl. So it could be the same alkyl group or different substituents. They are formed by the dehydration between the alcohol molecules. So you have two alcohol molecules that they do a dehydration, and you can form an ether. They are not very reactive, except like for combustion, like the alkanes, and they are very commonly used as solvent for organic reaction. Here we have the diethyl ether. We can see here we have the oxygen in the middle, the two R groups, the two alkyl groups, okay? And this one is with two carbons, is an ethyl. This one is two carbon, is an ethyl. That's why we have diethyl ether, okay? So 1, 2 ethyl, diethyl ether. Another very common is tetrahydrofuran, THF. This is very common in organic chemistry as a solvent. We have other functional groups that they contain their carbonyl group. The carbonyl group basically is a carbon double bond with oxygen. This is a carbonyl group. And we have 5 different groups that possess, or they have in common, that they have a carbonyl group. Okay, so one of these functional groups is the aldehyde, the ketones, carboxylic acid, the esters, and the amides. So these 5 groups are part of the functional groups that have carbonyl, the carbonyl group, okay, on them. So let's start with the aldehydes. The aldehydes and the ketones, they have at least one hydrogen atom attached to the carbonyl carbon atom. These are the aldehydes, okay? So the aldehydes at least needs to have one hydrogen attached to the carbonyl carbon atom. So we have here the formaldehyde or the methanol. We have one carbons, as if it was an alkane, it will be methane. But because of an aldehyde, the suffix is al, is methanol. So we have here methanol, and also here we have the aldehyde of 2 carbons, that is ethanol. Okay, so this is also known as acetaldehyde, the common name for this aldehyde. You can see that you have a carbon oxygen double bond. There's the carbonyl group with an hydrogen. So both of these are examples of aldehydes. The ketones have 2 R groups or 2 alkyl groups attached to the carbonyl carbon atom. Okay, so for example, here we have propanone or acetone. It has 2 R groups or 2 methyl groups. And here we have 2 butanone. We have the longest chain that has the carbonyl group is a 4 carbon, and this one is in position number 2, so that's why it's called 2-butanone, or also methyl ethyl ketone, methyl ethyl and ketone. And the third one is testosterone. There's also another very big molecule, but it has also a carbonyl group here. You can see there's a carbonyl group here with 2 alkyl groups at the sides, so this basically also is a ketone. Okay, so we have a ketone in the testosterone. So the difference between the ketone and the aldehydes is that the aldehydes in the carbonyl group needs to have at least one hydrogen. If you have both R groups, then you're talking about a ketone. Now, many aldehydes are natural flavoring. For example, vanilla, cinnamon, spearmint, and caraway, they are from aldehyde. So those really sweet smell are because of the aldehydes. Also the sweet flavors are because of the aldehydes. The ketones are used extensively as solvent. The most important solvent other than water is acetone, which dissolves in water and dissolve many organic compounds. So this basically also are some useful thoughts about the aldehydes and the ketones. Carboxylic acids. The carboxylic acid are formed by a hydroxyl group that is bond directly to the carbonyl group. So with the aldehydes, we need to have a hydrogen bond to the carbonyl group or attached to the carbonyl group. For the ketones, we need to have two R groups to that carbonyl group. For the carboxylic acid, we have an hydroxyl group, that is the group of the alcohols, the OH, attached directly to the carbonyl group. The hydrogen on the hydroxyl group is weakly acidic and important and the carboxylic acids are important in manufacturing polymers for films, fibers, and paints. And finally, the oxidation of alcohols produce the carboxylic acid. Sometimes they go first through aldehydes and then form the carboxylic acid, but we're going to see some examples now. Here we have the lactic acid, we have the carbonyl group, we have an R on this side, and we have an OH directly attached to the carbonyl. So this part is the functional group known as the carboxylic acid. So that's why this is lactic acid, because the acid basically is because of the presence of that carboxylic acid. Here we have the methanoic acid. Usually the suffix for carboxylic acid is OIC, oic, and we need to use the word acid. And this is methanoic because we have just one carbon, methanoic acid. Carboxylic acid again here. We have here the citric acid. In this one we have three carboxylic groups, okay, for this citric acid. Here we have the acetyl salicylic acid, also known as aspirin, and it has also here an carboxylic acid. That's why sometimes the aspirin has caused this refluxes in stomach, or like you feel like acid, and it's because aspirin is an acid. It has a carboxylic acid in their molecule. This one is ethanoic acid. We have a change of two carbon, okay, and ethanoic because it's a carboxylic acid, and acid because it's a carboxylic acid here. So we have here another example of a carboxylic acid, and finally the phenyl methanoic acid or benzoic acid, also with the functional group of the carboxylic acid. So if we have, for example, ethanol or any alcohol in the presence of an oxidation reagent, this will produce first an acetaldehyde. And then that acetaldehyde in those conditions will produce the acetic acid or the carboxylic acid. So from an alcohol, you can produce the aldehyde, and then the aldehyde can produce the carboxylic acid as the product of this reaction. The other functional group is called the esters, and the esters basically are products of reaction between carboxylic acid and alcohols. So when you react carboxylic acid and alcohol, you produce an esters. These ones are found in many fruits and perfumes. And the naming of the esters, you name the alcohol part as an alkyl name, and the separate word is the acid part as an anion. So in other words, we have here this ester. You can see here the carbonyl group, okay, of the ester, and this comes from an alcohol, okay. So basically here we have an ester. Instead of this is like a carboxylic acid, but instead of a hydrogen here, OH, we have an OR. Okay, so the esters are different from the carboxylic acid. The carboxylic acid is a carbonyl with OH, and the ester is a carbonyl with OR. Okay, and this part is the one you name them. You use this in an alkyl, so it's ethyl, and the other one, 1, 2, 3, 4, butyrate, is basically the base of the name. Okay, so butyrate is the name of the name, and ATE because it's an ester. So that will identify that it's an ester. The decomposition of esters, when you heat an ester in the presence of an acid, this will induce a reaction where it will decompose the ester, and with that, this will create a reaction that is called the saponification. So in other words, you are making soap. So one of the processes to produce soaps is from the decomposition of esters. So here we have an ester here, the carbonyl group and the OR. Okay, this in the presence of OH, it will break basically this bond. okay, and we attach this OH here and the hydrogen to the O of the methanol. So you will break this side and you will create the alcohol from here, and the um, uh, uh, salt of the carbolic acid, okay, carboxylate actually, that's what it's called, propionate, and the methanol. Because you're in a basic solution, you can't have an acid. That's why you don't have here a carboxylic acid, because you're doing the reaction in a basic condition. So once you create this uh, carboxylic acid, it will react with the base and you will create then the carboxylate, or the base, the weak base of conjugated base of the carboxylic acid. Okay, so from the ester, when is the you create the decomposition of the ester, you will create from this part the alcohol, and from this part the acetate, carboxylate, sorry, the carboxylate. So let's talk now about nitrogen containing organic compounds. These are the amines, and the amines are the organic derivatives of ammonia, ammonia NH3. One, two, or all three hydrogens atoms can be replaced by R groups. Okay, so these are the same, they could be the same or they could be different. So for example, here we have the ethylamine. So this one has substituted just one hydrogen from ammonia with an ethyl group. We have here, this one substitutes all three hydrogen for a methyl group, so that's why it's called trimethylamine. And this one is phenylamine, that is basically aniline. This is used for create amino acids also. And if H in NH3 or amines is replaced by a carbonyl group, okay, an amide is formed. So instead of one hydrogen, basically when you substitute that hydrogen for and attach directly to a carbonyl group, that one is called the amide. So an amide is the combination of amine and the carboxylic acid to produce this type of compound that is a carbonyl directly attached to a nitrogen. This is an amide. So our last topic for this module is chirality. And first, I'm going to discuss some specific characteristic of this chirality, and then we're going to talk about the importance, about why it's important to understand this concept. So first of all, carbons with 4 different groups attached to them are chiral. Remember that carbons can create from 2 bonds to 4 bonds, okay, the maximum of 4 bonds. So if you have 4 different groups attached to a carbon, that carbon is a chiral carbon, and also sometimes make the molecules also chiral. This type of compounds are optical isomers or enantiomers. So we have enantiomers that are optical isomers, that is due to the presence of a carbon with 4 different groups attached. The enantiomers have the same physical and chemical properties when they react with non-chiral agents. So you can see a difference between both of them, okay, because they have the same physical and chemical properties, even though they are isomers. So the enantiomers, one of the very different characteristic is that they rotate plane polarized light in opposite direction. One will rotate the plane polarized light to the left and the other one to the right, one to one side and one to the other one. So to try to explain what are chiral molecules, let's use our hands. If we put our hands side by side, we will think that they are the same because we have the 5 fingers, and we as we can see here, they look basically the same. And also, if we can put them like face to face, they look like a mirror image in front of them. Okay, so you see that, and you say, okay, they are basically they are the same. But when you try to superimpose them one over the other one, you can't. So that means that both of your hands, they are different, because if they were the same, you can overlap, you can superimpose them one over the other one. So the chiral molecules is the same concept. We have molecules that they look like a mirror image between them, and you can't superimpose one over the other one. So these are chiral molecules, and they are basically defined as one of them is going to be the L at the S, and the other one is going to be the R. Okay, so that's a name that you will understand why when you take organic chemistry. So one of them is going to be identified as the S enantiomer, and the other one is going to then be identified as the R enantiomer. Okay, and why this is important? This is important specifically for the development of drugs. Okay, many drugs are chiral compounds. Equal mixture of enantiomers is called a racemic mixture. Often, only one enantiomer is clinical active, and the other one can be inert or harmful. So that's why it's really important for us to understand the chirality, because if we create the wrong one, even though they look the same, the same uh, length and everything, and the bonds between them are the same, but this arranged in space is going to be different, and that will make one molecule different from the other one. One can be help us in some treatment, but the other one could be harmful. Here we have an example of this OH. This OH is in the front, and maybe this molecule is the one that is the clinical active. But if you put this OH in the back part, that could be harmful. Also, here we have this other one that has this hydrogen in the back. If you put this hydrogen in the front, that also will affect. It could affect this molecule. So that's why it's really important the chirality of molecules, the arrangement in space, okay, for the molecules is really important, specifically for pharmaceutical and development of drugs for treatments in diseases. So with this, we are finished our second module for chapter 24.